All right, so this last video for indicator 20 is indicator 20.4, and these are some special cases called perfect squares. So we're going to go through some examples. I want you to take notes in your 3-ring binder just as if you were in class. And then when you're done taking notes, click the load button at the bottom of the assignment, and it should pull up your assignment in Kami, and you'll show all of your work using either the pen tool or the text box tool, and then submit and submit to turn in this assignment. Okay. So just a little bit of an introduction here. So I told you these are some special cases. You'll notice, for one thing, these look a little different. These two right here, they look a little different because they're missing a middle term, right? There's an x squared, there's a number at the end, but there's no x value in the middle. So we're used to seeing quadratics, and what makes this a quadratic is the x squared, okay? But we're used to seeing quadratics with ax squared plus bx plus c. And what those look like with numbers in those places is something along the lines of 3x squared plus 2x plus 4. Or if there's not a number out front, right, we're used to just seeing x squared plus 4x plus 6. Okay, something along those lines. So these are quadratics. Well, you'll notice a quadratic has a squared value out front, a number in the C spot, but in this B spot, we're used to seeing a number. Well, what's missing here is that B, right? The BX or the B value is missing in both of these. And if you'll recall back to, I'm going to kind of take us back one indicator, we had something that looked like this. And I told you that this would come back and we would learn that this was something special called the difference of perfect squares. And so when we foiled this, right, if you think back to indicator, I think it was 18 when we learned about foiling, we did first, which was x squared. We did outer, so x times negative 4x is negative 4x. Then we did inner, 4 times x, which is positive 4x because it's positive 4 and positive x. And then we did the last, which is 4 times positive 4 times negative 4, which is negative 16. And then when you combine these like terms in the center, right, negative 4x and positive 4x canceled each other out. And so what it left behind was this. Okay, and I told you back then that we would learn that this is a special thing or a special case called a difference of perfect squares, where the two middle terms cancel each other out, and so when it reduces down to x squared minus 16 in this case. Okay, and what you'll notice about x squared minus 16 is that x squared is a perfect square because it is two exact things times itself, right? It's x times x. And 16 is a perfect square because it is 4 times 4. And so when you have a difference of perfect square, your binomial that it factors to is, let's see, do it in different colors. It's this x and this 4 with a plus sign, right? One of the x's, one of the 4's with a plus sign. And then it's the other x with the other 4, right? The other x with the other 4 and a negative sign. So we learned FOIL, and we learned to go from the binomial to the simplified the simplified version here. What we're going to be doing in this indicator is we're going to be going from here, and we're going to be going back up to the factored version. Okay, I know that's a lot of circles and lines and arrows, and so we'll do a couple of examples here, and I think it will make more sense. All right, so if you look at x squared minus 81, and remember what we're talking about here is we're talking about, we called these something special, and this is an example of a difference of perfect squares. Okay, this is one kind of special case. So if you look at, first of all, it's a difference problem because it's a minus sign. And then, are both terms perfect squares? Well, a perfect square means that two identical terms multiplied by each other. Well, we know that x squared is the same as x times x. So x squared is a perfect square because it's two exact x's. And we know that 81 is a perfect square because it is 9 times 9. So that means this is a special case. You don't have to do a factor sum table, nothing. Okay, if you recognize that everything's a perfect square, and I do want to point out, we don't ever write it. I'm not going to write it, but I'm just going to show you there's really a number in this A spot, and it's a 1. But 1 is also a perfect square because 1 is a perfect square because it's 1 times 1, right? Now, we are not going to write that 1 times 1. We're not going to worry about writing the 1 in front of the x, but just know that this really is a difference of perfect squares because the 1 is a perfect square, but we're going to ignore that 1 for right now. All right, so just like I showed you over here, right, when you have a difference of perfect squares, you take one x and one number. So I'm going to take the x and I'm going to take one of my 9's, and then I'm going to take my other x and my other 9. And remember, for a difference of perfect squares, it's very important that you have one plus and one minus, right? One plus and one minus. And why is it important? You have to have one plus and one minus. And I'll show you because we're going to refoil this out to test our answer, okay? So if I take FOIL and I do x times x, I get x squared. Then I take my outer, right, my x times my negative 9, and I get negative 9x. And then I take my inner, well, that's a positive. Positive 9 and positive x is positive 9x. And then the last thing is taking the last times the last, and a positive 9 and a negative 9 multiply together to give you negative 81. And then what happens, right, we know this from when we learned our FOIL lesson, is we combine these middle terms. But plus 9x and negative 9x cancel each other out. And so what you're left with is x squared minus 81, which is what we started out with up here. Okay, so it has to be 1 plus and 1 minus for two reasons. One, when you multiply the outer, you need it to be a negative 81, and the only way to get negative 81 is a plus 9 and a minus 9. And the other reason you need the signs to be a plus and a minus is because you need them right here. You need 1 plus and 1 minus to cancel each other out. Okay? So let me erase kind of all of this mess here so that we have a clear slate to work with here. All right, so let's look at example number 2. Okay, very straightforward. If you recognize right off the bat, it's a difference of perfect squares. No factor sum table needed, right? You're just going to go two binomials because your answer is always two binomials. And you're going to take, what is the square root of x squared? It's x times x. I do want you to put this underneath each perfect square. What's the square root of 1? Or the perfect square? 1 is a perfect square because it's 1 times 1. So it doesn't matter if it's a 1, if it's an x, if it's a 4. Think of all your perfect squares. 1, 4, 9, 16, 25, 36, all the way up, okay? And then x squared is a perfect square because it's x times x. So if you will do this little line right here where it's a difference problem because it's a negative sign, and if you will write the x times x under the x's, and you will write the 1 times 1 under the 1, when you do that, your answer should just kind of comes right to you. It's x plus 1, x minus 1. Okay? If I were to give you another one, you don't even have to write this one down in your notes. But if I said x squared minus 25, okay? right off the bat, you should recognize it's a special case because there's only two terms, and you should recognize that x squared is x times x, and 25 is 5 times 5, right? And it's a difference problem, so that means you can go right to your answer, which is x plus 5, x minus 5. And this works with every single one, right? If I do x squared minus 100, well, x squared is x times x, and 100 is 10 times 10. So I'm able to write my answer as x plus 10, x minus 10. Okay? And your perfect squares, right, are 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 and 5 is 25, 6 and 6 is 36, 7 and 7 is 49, 8 and 8 is 64, 9 and 9 is 81, 10 and 10 is 100. Of course, they go up from there. You can do 11 and 11, 12 and 12, but I don't think you'll see ones much higher than this. So these numbers right here, right, they're special because they are perfect squares. And so you kind of get to know them. And like if you see something that's two terms, you can pretty much bet that that last term is a perfect square. Okay? All right. So now let's look at an example where you actually have something other than a 1 out front. Thankfully, it does not change it, and it doesn't make it any harder as long as everything is still a perfect square. Is 4 one of your perfect squares? It is, because it is 2 times 2. N squared is a perfect square because it is n times n. It's a difference problem, so you're good there. And 81 is a perfect square because it is 9 times 9. So you still do this the same way, right? You still give yourself two brackets. And because the 4 and the n are together, your 2 and your n stay together. So 2n plus 9, right? I get that from there. And 2n minus 9. So it is still, right, one of these and one of these, and then one of these. So 2n plus 9, 2n minus 9. So you keep your minus sign here, right, is what should still separate everything, if that makes sense. So if you've got, say you've got 16n squared minus 64, right? Your minus sign stays the breaking point. And so when you factor on the left side, 16 and 16 is 4 times 4, and n is n times n, and then 64 is 8 times 8. This is where your plus or minus sign is going to go. And so your answer is going to be, right, these two. So 4n plus 8, and then 4n minus 8. So you'll notice the perfect squares on the left of your original minus sign go together, and then your plus and your minus sign breaks up your 8 on the other side. Okay, and hopefully I explained that right. Hopefully I explained that clear enough. I'll do one more example like that, just to make sure. And again, you don't have to write this last example down in your notes. I just want to do one more just to make sure that we are clear without so many squiggly lines everywhere. All right, so making one up, I've got 25. I'll quit using n because it's not always going to be n. 25r squared minus 49. Okay, it's a difference of perfect squares because 25 is perfect, r squared is perfect, 49 is perfect, and it's a difference problem. So I know that 25 is 5 times 5, and I know that r is r times r. Those two are going to stay together. Then on the other side of the minus sign, I know that 49 is 7 times 7. So in my answer, I'm going to keep my 5 and my r together. Oh, my pencil just shut off. There we go. I'm going to keep my 5 and my r together, and my 7 goes on the other side, right? And I'm going to keep my 5 and r together and my 7. And then what am I going to separate them with? A plus and a minus. Okay? All right. That's one special case. Now I want to look at this as a special case. Now, this won't jump out at you. This is not a difference of perfect squares, obviously. It's not a difference problem. It has a middle term. But if you happen to notice at the beginning, now you can do this the old-fashioned way, right? You can do the factor sum table, and you can take 9 times 64, which I don't even want to do that. I don't have my calculator with me right now. 9 times 64 is really big. And then your sum's going to have to be 48, and you're going to have to come up with a bazillion factors until you find the winning numbers and then all of that. But check it for the shortcut, okay? If you recognize that 9 is a perfect square, it's 3 and 3. And if you recognize that x is a perfect square because it's x times x. And 64 is a perfect square because it is 8 times 8. There is a shortcut, and I want to reiterate that it's a shortcut. If you manage to remember it and catch it, it'll just save you it'll save you all of this work over here, okay? If the front term and the last term are perfect squares, and this is how you have to test whether it works. 3 times 8 is 24. 3 times 8 is also 24. 24 plus 24 equals 48, which is your center term. If that happens, this is called a perfect square. It's not a difference of perfect squares, but it is called a perfect square. And because it's a perfect square, it's going to be 3x. Now it's plus and plus, so everything is plus. 3x plus 8, right? I got that from here, here, and here. And then the other one is also 3x plus 8, and I got that from here, here, and here. And you might see this written like this, 3x plus 8 squared. Now, I know that's a lot to remember. It's a shortcut. If you don't get there, okay, you would eventually figure out that, let me erase these, eventually when you go down the line of factor sum table, you would eventually get to 24 plus 24 multiplied by each other gives you your factor, and they add up to 48, and 24 and 24 would be your winning factors. And then you would replace 48x with 24x and 24x, and when you factored by grouping, you would get 3x plus 8 and 3x plus 8, and then you would write it like this. Okay, so this is a very unique case, and it only works when A and C are perfect squares, and when 3 times 8 is 24 and 3 times 8 is 24, and they add up to that center number. Let me see if I've got another example like that. I do. All right. Again, if you're looking at this, right, and you do your factor sum table, your factors would equal 900, and your sum would need to be negative 60. Those are pretty big numbers, and you could do it. You could get there. But if you happen to notice that 9 times 9 is 3, or that 9 is 3 times 3, and n, of course, is n times n, and then if you notice that 100 is 10 times 10, and then you check to see, right, if I take 3 times 10, right, 3 times 10 is 30, and then if I take 3 times 10, that's also 30. And, right, if I make both of these negative, then negative and negative adds up to negative 60, and the reason it needs to be negative, remember on my last one everything was positive, so my two center terms were positive. In this case, because this is a negative sign, they both have to be negative, but it still works the same way, okay? What you would find when you ran through this factor sum table is eventually you'd get to negative 30 times negative 30. Negative and a negative is positive 900. And negative 30 plus negative 30 is negative 60. So these would be your winning factors, okay? Now, because it's a special case and it's a perfect square, you can take 3n minus 10 and 3n minus 10. Now recognize on this one I took a minus sign because of this right here. But when I take negative 10 times negative 10, I still get positive 100. So it works out, okay? So when you have perfect squares, this term right here, that red arrow is pointing to, this determines whether or not both of them are negative. And then if you noticed on this one, this term right here was a positive, and so that made everything positive. Here, that term is a negative, and so it makes everything negative. And again, right, you would really see this on a multiple choice question written like this. Okay? Now, if that's too much, and if that's too much for you to try to think through and remember and catch, then don't let that throw you. You can do it like this with a factor sum table. Okay? If there are 3 terms, you can always do a factor sum table. The only time that you wouldn't really do a factor sum table ever at all is ones like number 1 and number 2, right? Where you don't have a middle term. You don't have a 3. You can't have a sum the center, right? Because your center is 0. So if this example right here, okay, and this example right here, if that was confusing and the whole perfect square special cases throws you, then just do it the way you know how to do it, which is the factor sum table. Find your winning factors, put them in the middle, factor by grouping, all of the stuff that we learned on Monday, okay? And then this one is just another one that's exactly the same, okay? This is really a 1, and 1 and 1 is 1 times 1. B is B times B. 1 is 1 times 1. And then again, you take 1 times 1 is 1. And you take 1 times 1 is also 1. And 1 plus 1 is 2, which equals that middle term. So this would be a special case. And because remember this sign right here determines whether or not they're both positive or they're both negative. So that means that your answer would be, and I'm going to write the 1 first and then I'll clean it up, would be 1b plus 1, 1b plus 1. That's taking this one, and this one, right? And then this one, and this one. And everything's a plus because of here. And again, to clean it up, you would not really write those first ones. So really, b plus 1 squared. But if you didn't catch that, and that's okay if you didn't, if you do the factor sum table, okay, and your factors have to equal up to plus 1, but they have to add up to plus 2. Obviously, 1 times 1 adds up to 2. So your winning factors are 1. Okay? So, and then because our leading term is a 1, right, you can go right to the answer, which is b plus 1 and b plus 1, which is exactly what we got. Okay? All right. So I know this was a lot. On your homework assignment, there's only 4 of them like this. And then the second half of your homework assignment is a review to get you ready for the quiz on Thursday. And on Wednesday, I will post the times of at least 2, possibly 3 Google meetings that I will hold throughout the day so that you can log in and you can ask me for help. I can help you with your review worksheet, which is what your, when you click on this assignment for today, the first 4 are 20.4. The second whole half of the worksheet is review from 20.2, 20.3, and 20.4. Okay, so the easy ones with just a 1 out front, and then the hard ones with the bigger numbers out front. I do really quickly want to show you something, and this will help you with your Khan Academies. Okay, it doesn't matter what order everything comes in. And what I mean by that is if I take and go 20, whoops, if I do 25 minus n squared, is this still a difference of perfect squares? It's a difference problem. 25 is perfect because it's 5 and 5. N squared is perfect because it's n times n. And so your answer, just keep it in this order, would be 5 plus n, 5 minus n. Okay, so if your original problem puts the number first and then the letter, just put the number first and then the letter in your brackets. Khan Academy throws this at you. So if you have 49 minus p squared, 49 is 7 and 7. P squared is p and p. So it would be 7 plus p, 7 minus p. Okay, if the number's first, write the number first in the bracket. If the variable is first, like in our examples here, right? Here the variable was first. Let me erase all this extra junk that we don't need. Just get down kind of the bare bones answer. Okay. X squared minus 81, the x's were first. So in your answer, you would put the x's first. The 81 was last, so you would put the number last. So just put them in the order. Khan Academy likes to throw them at you backwards, and they like to see if you're really paying attention, and sometimes they'll put the number first, and that just means you put the number first in your answer. All right, that's all I got for you. Again, log in on Wednesday. I'll post the times later on, either early Wednesday morning or late Tuesday night. I'll post the times of the meetings, and you can log in and ask for help if you need it. Have a good snow day. Keep warm.